Well, hello, physical science class. It is good to see all of you yet again. We've come into chapter 18 in our study together. It's actually the last chapter that we're going to be looking at this year, so congratulations, you've come here nearly to the finish line. I'm going to look at the first half of this chapter with you this week, and then we'll finish up the last half of it next week, and that will be the end of our physical science lectures this year. As a quick reminder to you, make sure that you do all the homework that's being assigned an I grade, as well as getting the tests done and into me whenever they are assigned. If you have anything outstanding that you have not gotten into me yet, please do that immediately and send that in. You either send it into my True North email address, or you can send it to jess@sojournbaptist.org. That's my church email. Either of those work. And I'd love to get anything in there that needs to be. And so please do reach out to me also if you have any additional questions through any of the lessons. I'd love to answer any of them that you might have. You just need to let me know. All right, so without further ado, let's get into chapter 18 together. So we'll be talking about principles of bonding in this chapter. I'm going to begin by just mentioning Colossians 3:14, which says, "Beyond all these things, put on love, which is the perfect bond of unity." We recognize that as Christians, we are bound together in the family of God by what Christ has done on our behalf, his death, burial, and resurrection, which we just celebrated in a very special way this last weekend with Easter Sunday. But it's the love of God that's been poured out into our hearts that now we show to one another, and has formed our unity and our community together. And so we know that that love is bonding us together. Well, we're going to be talking about chemical bonds and about the ways in which different elements find unity with one another through the pairing and sharing of electrons. The second law of thermodynamics tells us that things tend to lose energy. Remember, this is kind of like a ball sitting at the top of a hill. It will tend to roll down to the bottom of the hill until it gets to a valley, into a place of lowest energy, right? Lowest potential energy. An atom naturally minimizes how much energy it has, and as a result of this, atoms bond because they lose energy and they gain stability. So the reason why elements come together and atoms form bonds is because through this they lose energy and they gain more stability. The arrangement and number of electrons in atoms determine how they bond. We're going to be looking at various types of bonds in this chapter. The same element with the same electron structure can often bond in more than one arrangement. One of the best examples given of this is graphite and diamond. Now, both graphite and diamond are just made up of carbon. On page 413 in your book, you'll see a great picture of graphite sitting right next to diamond. Both of them are just an arrangement of carbon atoms. One, something that seems to be not all that valuable in general to us, but another one that's highly prized as a piece of jewelry. Graphite and diamond are actually both very important in their respective fields, but very, very different, and all based upon the structure of how these bonds happen together. Chemical bonds involve mainly the valence electrons of an atom. So within an atom, you have to remember the nucleus has the protons and neutrons there in that densely packed core. And then you have these electrons that are outside of that. And depending on how many electrons there are, some of those electrons are close to the nucleus, and some of them are further out in higher and higher energy levels. And so the electrons that are involved in chemical bonds are those on the outside levels, the highest levels of energy level around the atoms. And these are the electrons, because of the outside, they're called valence electrons, which are involved in bonding with other atoms. So the octet rule tells us that atoms are generally more stable when they have a full 8 electrons in their valence energy level. It's called octet because of the number 8. So you're going to see with me in coming examples that atoms try to achieve a full outer shell, which in most cases means 8. There are a couple of exceptions, like hydrogen, for example, which just wants to get to 2. But for pretty much everything else in general, they're trying to achieve 8 electrons in their outer shell, or their valence electrons. Quick mention about electron affinity and electronegativity. Electron affinity is a measure of how well the atom attracts and holds electrons. If it has a positive affinity, that means that energy must be added for the element to take electrons. If it has a negative affinity, it means the element gives off energy when it gains electrons. So if it has a positive affinity, you're having to put energy in order for that atom to take on more electrons than it already does. If it has a negative affinity, it means that the element already wants to take on additional electrons, and it will release energy whenever that occurs. Metals have very low affinities. Some are positive or negative values. They have very low affinities, whereas halogens and most nonmetals have negative affinities. So halogens and nonmetals usually want to take on electrons, whereas metals typically you have to put energy in order for them to take on them. Now, electronegativity is a scale which is used to compare an atom's ability to attract and hold electrons when bonded to other atoms. Generally, this electronegativity is higher when the valence level is nearly full. In other words, when they're almost all the way full, they're even more desiresome to take on just one more electron so they can actually fill out that 8 valence electrons. If they're far away from 8, if they only have like 1 or 2, for example, then that electronegativity is going to be much, much smaller. In fact, in general, they might even want to give away those electrons in order to go down to a lower shell that might have a full valence of 8. So electronegativity is just a scale that's used to compare one atom's ability to attract and hold electrons when compared with other atoms that are trying to attract and hold electrons. So there are a couple of different types of chemical bonds. There are covalent bonds, in which there's more of an equal sharing of electrons. Usually this is happening between nonmetals on the periodic table. Remember, nonmetals are found on the right side of the periodic table, whereas the metals are found on the left side of the periodic table. Usually when atoms have large electronegativities, they have more of a covalent situation. An ionic bond, it happens whenever there's a little bit more of a give and take relationship. Rather than sharing so much, one atom is really wanting the electrons a lot more than the other atom is. This is called ionic, and this usually happens between a metal and a nonmetal. So again, something from the left side of the periodic table combining with something on the right side of the periodic table. Usually when atoms have very different electronegativities, where one wants electrons a lot and another one doesn't want the electrons so much, that's usually where you have ionic bonds happening. And then you have metallic bonds. So you have covalent, you have ionic, and you have metallic. And so we said that covalent are usually nonmetals with nonmetals. Ionic are usually metals with nonmetals. So then you can kind of guess. Metallic bonds must be metals with metals. In this case, there's a sharing of easily lost electrons, usually here in metals. And usually when atoms have weak electronegativities. In other words, none of these elements are really trying to grab or hold on to their electrons so much. There's kind of like this free sea of electrons that are allowed to move about. All right, so this brings us to section B and talking about covalent bonds. We'll talk about this time, and then next time we'll talk about ionic bonds and we'll talk about metallic bonds. A covalent bond exists between only 2 atoms, but an atom can form multiple covalent bonds at the same time. So a covalent bond is just happening between 2 atoms, but just note that one atom can have multiple covalent bonds attached to it with other atoms. Covalent bonds, as I already said, usually are nonmetals. They usually have little or no difference. That's what the triangle here means, difference in electronegativity. En means electronegativity. So therefore, these atoms share electrons. So when the difference in electronegativity between the things is not very great, that means that there's not one wanting them a whole lot more than another one. That means they're going to share these. And so these bonds are described as covalent. The two shared electrons are called a bonding pair. So electrons often will share as a pair. And so it's called a bonding pair whenever these electrons are shared between atoms. They are located between the atoms most of the time. The negative region between the atoms attracts the nuclei with an electrostatic force. So the way that this is pictured in chemistry is by the use of Lewis structures, sometimes called dot diagrams. And we only show the valence electrons. That's the only ones that we show when we're drawing these dots. We don't draw the dots that are closer to the nucleus. It's just always the ones on the outside. Remember, with that magic number 8. So it's usually going to be a number of dots from 1 to 8 that we're going to symbolically represent these electrons with. So we'll then use a dash to represent a bonding pair. So whenever two dots come together between two atoms to form a bond, we're going to replace the two dots with a dash, showing that that's a bond between the atoms. Now, there are diatomic elements, which means that these elements will bond with themselves. You don't find them by themselves when you have, for example, a hydrogen atom. It will just bond with another hydrogen atom to make H2. Same thing with nitrogen and oxygen, fluorine, chlorine, bromine, iodine. These all are diatomic because there are two atoms of each of these things as they combine together. Now, you'll see that I've also notated here that with nitrogen, there's a triple bond, and with oxygen, there is a double bond. So hydrogen's diatomic state would be seen this way, H dash H. Remember, this dash symbolizes one bond, symbolizes one pair of electrons being shared. With nitrogen, though, there's actually a triple bond, and then an additional pair of electrons, which we would show by dots, looking like that. With oxygen, there is a double bond, and as a result, there are then two pairs of electrons on each of the oxygens that are all already there, but then there's two pairs being shared here. Whereas with nitrogen, there are actually three pairs of electrons being shared between the nitrogen, and then they just have an additional set of electrons on the outside. So hydrogen has a single, the hydrogen bond here, diatomic, is a single. Nitrogen's a triple, oxygen's a double. Fluorine, chlorine, bromine, iodine are all singles, just like the hydrogen bond up here. The way you can remember the diatomic elements on the periodic table is HNO halogens. It's hydrogen, nitrogen, oxygen, and then the halogen group, which are found on the row 7A on the periodic table. Remember, row 8A, we find the noble gases, right? So the noble gases are found on 8A. The one right before that, 7A, are the halogens, which is fluorine, chlorine, bromine, iodine. All right, so diatomic, as I just said, means containing just two atoms. And single bond examples are chlorine and hydrogen, whereas double bonds and triple bonds are found in the case of oxygen and nitrogen, respectively. So again, here's the way that could be pictured. If we were picturing it with Lewis dots, Lewis diagrams, which I will show you in just a moment how we actually do these. But note here with hydrogen, hydrogen only has one electron. It's got one proton and one electron in its ground state. So here, the one dot from each hydrogen comes together here in the middle, which then gets moved into just a single dash line showing that this is a single bond. With oxygen, note, we've got 1, 2, 3, 4, 5, 6 electrons in each of these oxygens. It is in column 6A, which makes sense of that. And so then this pair of electrons and this pair of electrons join together to make this and to make these bonds. So it looks like a double bond. In nitrogen case, it's in the 5A column. And note here, we've got 1, 2, 3, 4, 5. We've got 5 dots. So then what we have is we've got 3 pairs of electrons. Those two pair up, those two pair up, and these two pair up, which gives us then a triple bond situation for nitrogen right here. In general, for nonmetal elements, the number of unpaired dots is the same as the number of covalent bonds that the atom can form with other atoms. So the more unpaired dots there are, the more possibilities for bonds there are. So let's look at the example of H2CO. So what we'll first do, if we're going to write the Lewis structure for this molecule, we'll show first of all hydrogen. So hydrogen is on column 1A of the periodic table. He's H, and he's got just one dot for that one electron. Carbon is found on the 4A column. And so you'll see here, remember from our learning how we draw these the dots, we start with the right side and we draw 1 and 2. So we do these two first, and then we draw in 3 and 4. Oxygen is in 6A, so it has 6 electrons in its outer shell. And so again, we start here 1, 2, and then we would write 3, 4, 5, and then we start pairing up this one 6. So this is each element dots with its dot symbols for the valence electrons: hydrogen, carbon, and oxygen. Then we determine how many valence electrons are available. Well, hydrogen has 2. Remember, because we have 2 hydrogens, right? There's 2 of these hydrogens. Carbon has 4, and oxygen has 6. So we have a total of 12 electrons. Now, we will always place the largest number of unpaired electrons in the center of the structure. Now, we have repositioned one of the dots. Remember, we would have drawn a dot right here, but instead we've moved it to down here to show that there's actually 4 electrons that could find bonds. And just as a hint, if you ever have a molecule with a carbon is almost always like centered in the molecule. We write him down first because he's going to have lots and lots of opportunities for bonds. Then note, if we put in a hydrogen above and to the side with its electron dot, you see here that we now have paired these two up. And then we have oxygen, which had 6. We could pair these two and these two. So we place these remaining elements around that central atom, and then we start pairing them up, just like I just did. And notice that the hydrogen pairs nicely, and then with the oxygen, we make one bond. But notice we still have an electron here, a dot, and a here, and they would like to still pair up. And in this case, that's exactly what they do. We create, first of all, as many single bonds as possible, and then where we can, we create a second bond. And so this is how this would kind of look. We have a double bond between carbon and oxygen, and then remember, these are pairs of electrons, are just fine and content just as they are. And then hydrogen, remember, maxes out actually at 2, and so he's fine there because he's sharing with the carbon in each of those spots. So it would look kind of like that or that. And we can check by counting up total number of electrons. This is, by the way, formaldehyde, but we count up the electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have all 12 electrons represented in this picture, right? 2 for each of these lines, so 2, 4, 6, 8, and then 10, 12. Just to show you an example of water, here we have 2 hydrogen atoms combining with an oxygen atom. Now note here that oxygen actually has 8 protons in the nucleus, and it has 8 electrons. But the first 2 are in the first energy level, and they're closer to the nucleus. So the only ones that we're concerned about are the one on this outer shell here, which, as you can see, have 1, 2, 3, 4, 5, 6. Okay? So then these 6 electrons, these 2 hydrogens, come and bond in these locations, where then they can share these 2 and share these 2, which is demonstrated down here, and can be then rewritten in this way. Now, you could leave it just like this, or you could write, again, show those other 2 pairs of electrons, these 4 right here. You can show them as still dots if you like to. Either way is an acceptable way of drawing water. Here's ammonia. We have 3 hydrogens, all with a single electron, and then nitrogen. Note here, nitrogen has these 2 on the inner energy level, but on its outer shell, it's got 1, 2, 3, 4, 5 electrons. So that means that there's already a pair together, and then there's 3 others that would be happy to bond with something else. And sure enough, that's what happens here. Each of these hydrogens combines with one of those unpaired, making all of these into paired situations. So then it kind of looks like this, which then can be rewritten as this. And again, you could write with the nitrogen pair of electrons sitting right there. You could also draw it that way with dots right there next to the nitrogen, showing the other pair. Here's an example of methanol. Again, the molecule looks bigger, but it's the same principles involved. We have 4 hydrogen atoms, each with 1 electron each. We have the carbon with 4 electrons and an oxygen with 6. And so we put the carbon here in the middle. We can put an H to either to the other 3 sites here with an oxygen here. And then oxygen, remember, makes a single bond here with the carbon. It has 1 more electron left, and so we can take that remaining hydrogen and attach him to the oxygen down here, such that the end molecule looks like this. And again, you could show those other 2 pairs of electrons like that if you so wanted. Okay, now if the difference in electronegativity numbers in a covalent bond is 0, that means you have a perfectly diatomic thing. You have hydrogen with hydrogen, because hydrogen desires electrons the same amount as another hydrogen atom. They both desire electrons the exact same amount. So there's a net 0 difference in electronegativity between the 2 hydrogen atoms, which means that it's a very nonpolar bond. By nonpolar, we mean there's not one side of the molecule pulling the electrons more than another side. So the whole molecule is very balanced. So take, for example, the hydrogen molecule, an H with an H, or the fluorine molecule, a fluorine with a fluorine. They both equally share the electrons. Okay, they both pulling, if there was a tug of war, they're both pulling with the exact same amount of strength. And so as a result, it's a very balanced molecule. They're sharing equally. But if the difference of electronegativity is greater than 0, then the electrons are shared in an unequal fashion between the atoms. This then forms what's called a polar covalent bond, which means there's a part of the molecule that is either more negative or more positive than the other. Hydrogen often forms highly polar covalent bonds. So take, for example, this one, hydrogen with fluorine. In the HF bond, the shared electron is pulled much closer to fluorine. Fluorine is wanting to grab at that electron a lot more than hydrogen. So in a sense, they're still sharing, there's still a bond, but fluorine is pulling it more than hydrogen is. The electron is closer to the fluorine than it is to the hydrogen. The F end is partially negative, which gives it a polar negative charge, while the H end, the hydrogen end, is partially positive, giving it some positive charge. So it would look something like this if we were going to depict it. This fluorine is pulling that electron more towards itself, plus this fluorine also has 3 other pairs of electrons on this side. So this part of the molecule is very negative, while this part of the molecule is positive. So it's a polar molecule because it has poles, a positive and a negative end. So this is kind of what it looked like comparatively. A covalent diatomic molecule, nonpolar, looks like this, very, very symmetrical. A polar covalent bond looks like this, where there's an area that's more positive and one that's more negative. An ionic bond, it says here no electron sharing. It's not technically no sharing at all, but roughly there's not much sharing at all because one of these things is really pulling the electron and is pretty willing to give it up. So we'll be talking about ionic bonds next time together. Just one last slide talking about some properties of covalent compounds. There's a weaker attraction between molecules compared to ionic compounds, which affects their physical properties. Most have relatively low melting points. Many are liquids or gases under standard conditions. So a lot of these covalent compounds are liquids or gases, which is where it will make a big difference when we look at the ionic compounds and look at metallic compounds. Most of those are solids under standard conditions. Well, that's the last slide for sections A and B in Chapter 18. Make sure that you do read those sections and complete the questions at the end of each of those. I have included the answers to those for you to work on, to check yourself, to make sure that you're on the right track. Next week, we'll finish up this chapter and finish up our lectures for this year in physical science. Please do reach out to me if you guys have any additional questions, if you need any help at all. I'm here and love to help you any way I can. God bless you guys. See you soon.